hosting us and for being so generous with having us, me and my group here. So today I just want to give you a brief overview of the kind of two projects that we're working on with my group at LSU. Tomorrow we have two separate talks from Guru and Shagib that are sitting right there, my two postdocs, who are going to specifically talk about their individual projects. And what I've been fascinated about over the entirety of my postgraduate career is things that change in the sky in several timescales ranging from days to several months, in some cases years. And what amazes me when I study things that change or transient astrophysical phenomena is the diversity of luminosity, spectral properties, features that come along with this new class of explosions called superluminous supernovae, among other things that I'm going to talk about. And what I like to show every time I start this presentation is one of my favorite objects in the Milky Way galaxy, namely, as every single one of you here knows, the Eta Carina bipolar nebula. And what that represents is an extreme case of mass loss around massive stars. In this particular case, you actually have a binary system of stars, and something happened back in the 1800s, formulating and creating this complicated homunculus nebula around the system. And the whole purpose of this picture is to just show you that the environments around massive stars are way more complicated than we once thought, and they actually affect the way that these stars die in some very particular cases. So I don't know why I cannot go to the next slide. There we go. So just to demonstrate further the point that I'm trying to make is that the environments around massive stars we know today tend to be very untidy. Forget about this textbook picture of stars embedded in clean, dark space in the vastness of space. Quite more often, you have environments like this. You have complicated wind nebula, wind-blown nebulae, and strong circumstellar patchy shells like this, bubbles like that, as well as all kinds of interstellar matter around the circumstellar material that is created by the star itself in the years, quite often, in the billions of years before the explosion, but quite often also in the days to months before they explode. So considering the complexity of environments around massive stars, we have to go back to the drawing board, and we have to rethink the way we study how those stars die, how they explode, and how bright they get once they do so. Another favorite object of mine, if you study supernovae, it's always going to be your favorite supernova, is supernova 9087A. So complicated environments can lead to quite messy endings. And this is very nicely illustrated in the case of supernova 9087A, where here you see nearly 4 decades of data collected from the Hubble Space Telescope that show you the entire evolution of the supernova ejecta, which is this bluish American football shaped thing that you see in the middle. But if you look closely, you also notice a clumpy ring around the ejecta that over time gets brighter and brighter as the supernova shock wave rams, sweeps up material into this surrounding ring. Now, you may start wondering, what in the world? What created this weird environment around the progenitor of supernova 9087A? Was it the star itself? Was it a companion star that somehow interacted or merged, perhaps, with the progenitor 9087A? This is the leading theory we have today, that supernova 9087A was actually a star that experienced the merger in the years prior to the explosion. And as a result of that merger, it lost some material that remained around it in the form of a ring. And then eventually, when the explosion happened, it interacted with this ring. So when you're thinking about circumstellar environments around massive stars, you can literally have anything you want. It's a zoo. You have all kinds of environments ranging from shells to disks, to clumpy rings, to spiral-looking things, to bipolar nebula like Eta Carina. You got all kinds of geometries. So the problem is inherently three-dimensional. traditional spherically symmetric thinking need not apply in this situation. That means that you need to study the problem in 2D and in the easy case, and in the best case, three-dimensional geometry by performing rigorous hydrodynamic simulations of what happens once a star explodes and interacts with the surrounding material. And that means that you're going to have to deal with the need of a lot of computing time, access to large supercomputing resources, and with computing problems relating to many complications, including the very simple thing of needing to resolve the photosphere, which again is not going to be spherically symmetric in any of those cases correctly, such that you can get an accurate prediction that you can compare with observations, such as a light curve. So there's a lot of complications. It's easier said than done. And another way to put this is if you look into the space, that the plot that's commonly used by people that care about circumstellar interaction, whereby in the y-axis you have the mass loss rate measured in log solar masses per year, and in the x-axis you have the expansion speed of this circumstellar material. So obviously down here you got typical red supergiant, yellow supergiant wing, AGB winds. And as you go towards the right and the top of this diagram, you have the most extreme environments, which are Eta Carina-like luminous blue variable LBV environments. And for those environments, it's impossible to create a circumstellar environment just by simple steady state wind over the course of billions of years, like the red supergiant star will do. For those environments, you need eruptions. You need episodic mass loss phenomena. So the question is, of course, a major question of modern stellar evolution. You know, stellar evolution is fascinating. For many years, we thought it was a solved problem. Then we learned that toward the end of the evolution of massive stars, there's a lot of hydrodynamic things that are taking place that are removing mass from the progenitor star. And then, of course, add another star into the system, into a binary interaction. And then you got a lot of complications. So stellar evolution is far from resolved if you consider this kind of effects. Anyhow, you can have situations where massive stars abruptly lose a lot of material. And that material is not going to disappear. It's going to sit around the star. And that star is going to blow up as a supernova and interact with it. So this is a space that I'm interested in particularly. And it's a space where you find some of the brightest transient phenomena in the universe, including superluminous supernovae and other fast luminous transients that I will talk about today. So speaking of superluminous supernova, from now on, I'll be using the SLSN acronym. We broadly categorize them in two types by using the standard way that astronomers have been using for many years to divide types of supernovae. If you see lines of hydrogen, then that is a type 2 hydrogen-rich superluminous supernova. If you don't see lines of hydrogen in the spectra, that's a hydrogen-poor superluminous type 1 phenomenon. So here, when I say hydrogen, that comes in the form of very prominent emission lines of Balmer series. So you got H alpha, you got H beta, typically seen in interacting supernovae. Now, there is a low luminosity equivalent of this, which is called a type 2N supernova, where N stands for narrow, which is the width of the emission line. Type 2N are interacting supernovae. And in this situation, the reason you get those lines is because you have a shock wave that's propagating into the circumstellar wind, reionizing hydrogen, which then recombines, producing this feature. That's a recombination feature. In 2/3 of the currently observed supernova sample, about 65%, you do not see hydrogen lines. You see other features or no features at all. That's a hydrogen-poor superluminous supernovae, which is the majority of cases. The question now becomes, okay, just because you don't see signs of interaction, does that mean that interaction does not power the luminosity that you see in this bright superluminous type 1? That is an open question that we're trying to resolve with my group. The other thing that I want to put attention to, and you see some light curves on the top here for both categories. Now, what's fascinating about this events is that they have a wide variety of observables, of the diversity of observables. For example, you see some superluminous supernova that take about 70 days to reach the peak luminosity, whereas you also see some events that take about a week to get to peak luminosity and then decline really fast. The peak luminosities themselves range dramatically. The durations of the light curves, the shapes of the light curves range in this phenomenon. It's a zoo. It's a very complicated, very diverse class of astrophysical class transients. So the question is, what is the source of this diversity? Is there a mechanism which powers the extreme luminosity of superluminous supernova that's dominant? Are there many mechanisms at play? Or this is the natural result of the diverse environments you can have around massive stars? And that's a big question we're trying to address. So here's some pressing questions, some burning questions in the superluminous supernova community that we're trying to solve with rigorous hydrodynamics and radiation transport simulations. What fraction of the observed population of superluminous supernovae is powered by interaction? CSI stands for circumstellar interaction in this case. There's other models out there that the community has proposed as to the source of this phenomenon. One of them is the rapid spin down of a newly born magnetar, for example. It's a competing model. Another one is apparent stability supernova that blows up and produces several tens of solar masses of radioactive nickel-56, which can then power some of these explosions. But those stars are very rare. We're talking about 100, 200 solar mass stars. Another competing model is the accretion fallback model, where you have a little bit of matter left over in the ejecta after the explosion that falls back into a newly born black hole, but then accretion power can provide you with extra source of energy to reach superluminous levels. So the question is, which model is dominant when it comes to this phenomenon? What are the effects of circumstellar interaction on the spectra of superluminous supernovae? How does composition of the circumstellar environment, geometry, the density affect what you see as a light curve? Can hydrogen poor events, which do not show traditionally clear signs of interaction, actually be powered by interaction? You just don't see it if the conditions are not right to create emission lines. Can circumstellar interaction formulate the basis of a unified, and whenever I use the term unified in our field, I like to put quotation marks around it because it's quite a strong statement, in my opinion, model for superluminous supernovae, whereby the diversity of all the light curves and spectra that you see is a natural manifestations of different CSI compositions, geometries, viewing angles, and so forth. And what can we learn? How we decipher the mass-loss histories of massive stars by studying superluminous supernovae? Another category of transient that I'm interested in is those transients called supernova impostors. And as the name suggests, those are transients that kind of trick you. You think that there's been an explosion, but then there's another outburst coming from the exact same source. It could be actually several outbursts prior to the real explosion. And for this particular event, Supernova 2009 IP, we're not actually even sure if actually that represents its real final explosion. So from one source, you could have multiple transients. What's going on there? Are there episodes of mass loss taking place? Is there some sort of interaction between previously ejected cells that is taking place? What is driving this mass loss, producing those transients? That's another question. And then you have the real weird transients, which, by the way, with the advent of the Vera Rubin / SLSNe telescope, we will find a lot of. We're expecting to discover 1 million transients per night with LSST. A lot of those will be very weird transients we've never encountered before. For example, you have this event right here, IPTF 14HLS, which, as you can see, this is a light curve, right? It lasts for about 600 days. That's nearly 2 years of evolution. And during those 600 days, you've got several undulations in the light curve. Now, if you take a spectrum, which they have, right, during this time, it looks like a plain vanilla type 2P supernova explosion. The exact, features that you would see in a red supergiant type 2P explosion, you will see right here. However, the flux doesn't behave at all like you would expect for a type 2P supernova, which has a 100-day plateau that then rapidly falls off into a radioactive tail. So what's going on here? Then you have other things like KSN 2015K, which is a Kepler discovered transient that lasted for only 10 days. Whoop, goes up and then disappears. Very fast. Transient, which is also called FELT, fast evolving luminous transient. And you have some of those transients that are very blue in color. Those are called fast blue optical transients. And then you could also have situations where you have a smaller star merging with a bigger star, undergoing common envelope, ejecting some of this as a result of depositing energy into the envelope of the primary star, ejecting part of that envelope and producing a luminous output or a bright output. Those are called merge bursts. And actually, this is a term coined by Noam Soker from Israel, who used to be one of my postdocs supervisors back in the day. So now let's talk a little bit about the physics, okay? So you have all these weird transients, superluminous supernovae, supernova impostors, episodic mass ejection phenomena, merge bursts. What do you see when you look at spectra, light curves? Well, I showed you several examples of light curves, but now I want to hone into the spectral features a little bit. So on the right here, you see an observed line profile for one of the most well-studied type 2 superluminous supernova, Supernova 2061. So this is the H alpha line. And as you can see, it's not symmetric in shape. It's suppressed towards the blue. It's got a narrow absorption component at about 200 kilometers per second, a narrow emission component, and then a broad emission component. This is what that looks like during around peak luminosity. That spectrum was taken at about the peak luminosity of Supernova 2061. Now, when you have interaction, this is a very textbook standard picture that you will see, where you have the supernova ejecta. It slams into, in this particular case for simplicity, a spherical shell that leads to the formation of what we call a double shock structure, where you have a forward shock that's moving into the ejecta, into the circumstellar envelope, a reverse shock that recedes back into the supernova ejecta, and together in this simplistic one-dimensional geometry, they bound a density peak, which is called a cold dense shell. So you have a density peak that's swept up right in between this double shock structure. So you have several kinds of domains here, right? Further out, you got the slow moving wind that was there from the main sequence years, let's say, or the Wolf-Rayet years of a massive star, say about 200 kilometers per second of wind. Right here, you have a high velocity region, a shocked high velocity region that can be up to 5,000 kilometers per second in speed. And then back here, you have an even faster moving supernova ejecta, which could be up to 10, 15, 20,000 kilometers per second. So you have regions of multiple velocities, multiple properties. That means you have photons that are arriving to your detector from different regions. And the combined effect of getting photons from here, from all different regions is this line profile shape that I'm showing you here. So for example, with number 1, I'm showing you the narrow absorption component, which is produced by photons directly emanating, absorbing light and photons from the photosphere, from the wind. So this is the wind absorbing photons at this particular speed. On 4, you got photons emanating from the shocked high velocity region, so that you have a broad line component, emission component. So you can see how those different regions correspond to different parts of this line profile here. Now, forget about the spherical symmetry and think about something like this for a second. And why would you think about something like this, where you have a progenitor embedded in a non-spherically symmetric circumstellar environment. In this particular case, you've got a disk around your progenitor star. Well, you would think about geometries like this because, as it turns out, they found a couple of transients, PTF 11 IQB and Supernova 2018 BSZ, which have a very weird line profile evolution. This is the line profile evolution ranging from day 2 up to day 193 for one of those two transients. I think this particular one is 2018 BSZ. And as you can see, it starts with typical, more or less symmetric emission lines of H alpha, hydrogen. And as time goes by, something really weird happens. It starts developing a blue bump over time. So how do you explain that? You don't see that in other transients of the interacting type too often. Well, one way to explain this is by invoking a non-spherically symmetric geometry, which is what Nathan Smith here has done in his 2015 paper. In this case, you got a progenitor, it's got some red supergiant wind and a thick circumstellar disk around it. After the explosion takes place, early on, within the first 20 days or so, you have early interaction with the disk part of the CSI. So whenever you see those frames here, the dashed red line corresponds to the location of the forward shock, and the solid black line corresponds to the location of the photosphere. So early on, your photosphere is inside your wind. That means you're going to see line features typical of Wolf-Rayet winds. Later on, as the interaction goes on and the supernova ejecta expands, by the way, you have more expansion towards the polar sides than you have towards the equator because of the interaction, you will have the photosphere receding and the forward shock expanding further out. So you will be sensitive to radiation coming from several regions, including broadline regions, because you'll be able to see photons coming directly from the supernova ejecta. So you will start seeing the broadening of the wings of the emission line. And then as time goes on, at a late time, then your photosphere pretty much will be gone. You'll be completely receded into the inner ejecta, but your forward shock will keep going further away. So you will, at this point, produce a lot of emission lines, kind of like a supernova remnant emission line spectrum, narrow emission lines, which is what you see later on. So that's the way to explain this evolution of this line profile, potentially. But of course, what they've done in this paper is a cartoon kind of explanation. They haven't really done a numerical model to illustrate this. And that's the whole thing that we're trying to accomplish with our work. Now, when you think about interaction, the reason that it's been really hard to study, and when I say study, I'm focusing on radiation transport. Radiation transport formulates the basis of making predictions that you can validate with your telescopes, right? So we want to make predictions of light curves and spectra and line profiles as a function of time for a variety of transients. Okay, that's the goal. Why is that so complicated? After all, there's so many codes in the marketplace that people have used for years successfully to model supernova explosions. Well, because those codes are making several simplifying assumptions that dramatically and miserably break down in the case of interacting supernova. The first such assumption is the assumption of homologous expansion. When you have a supernova ejecta, it expands homologously like a Hubble flow. That simplifies the radiation transport aspect and the assumptions you can make to calculate spectra numerically. And you can do that for type 2P supernovae, type 1A supernovae, and get pretty good predictions. But once you talk about interacting supernovae, all that breaks down. And this is the reason why. This is the velocity profile from a radiation hydrodynamic simulation of an interacting supernova. In this case, we got 18 solar masses of ejecta interacting with about 0.2 solar masses of circumstellar material. The progenitor was a red supergiant star of about 600 solar radii, and the implied mass loss rate for the wind was 0.025 solar masses per year. So the red here gives you the distribution of velocity as a function of radius, and the green gives you the distribution of density as a function of radius. This is the cold dense shell I was talking about earlier, this density spike that you see in 1D radiation hydrodynamic simulations of interaction. And your photosphere is represented by this vertical dashed line here. It's right in a region of high velocity, negative velocity gradient, as well as a region of relatively low density. There's nothing homologous about where your photons are going to come from in this particular situation. That means that your Sobolev approximation, another quite commonly used assumption in radiation transfer codes for supernova exposures, completely breaks down. You can have more than one interaction points for your photons because of this complicated velocity structure. And the velocity gradient, as I said, in the line formation region can have large negative bias. So that means you have to resolve this region to the best of your ability. If it's under-resolved, your predictions are going to be pretty bad. So that's the first complicating physics. The second one is that you have strong non-local thermodynamic equilibrium conditions, or NLTE conditions. And this is because you will have the radiation temperature of your gas ahead of the shock in the circumstellar material, and the gas temperature being drastically different. They're not in equilibrium. In those lower density regions ahead of the shock, they're not going to be in equilibrium. So here's your radiation temperature with red, and this is your gas temperature with black. So that requires NLT treatment for level populations and ionization and so on and so forth, which can be extremely complicated and consuming computationally. There's only a few codes that do real NLT treatment. A lot of codes are fudging it by using a prescription called the nebular approximation, which is what we've implemented, and we're working towards at least adding true NLT for the most important species, in this case, hydrogen, because we care about the hydrogen lines. So again, that bears the question. We do see hydrogen recombination lines in hydrogen-rich superluminous events, but there's maybe one or two situations where we've seen narrow emission lines of helium, carbon, oxygen for some transients. Does that mean that most, if not all, of hydrogen-4 superluminous supernovae are not powered by circumstellar interaction, or is it possible to produce them to have hydrogen-4 circumstellar interaction, but somehow hide those spectral features? If you don't include those NLT assumptions correctly, you're never going to be able to truly answer this question. The third complicating effect is that because you have this high density spike in a highly shocked environment following this interaction, your Thomson scattering optical depth is going to be greater than 1, especially early on during the interaction, which means that a lot of your photons are going to undergo multiple electron scatterings before they free stream toward the observer. And that in turn means that will affect the width of your line profile. So as you can see here, this is an experiment, a Monte Carlo experiment, where you have a line shown here with gas curve with no electron scattering, and then you increase the electron scattering optical depth. And as a result, you start displacing more and more photons towards the wings, and your wings become broader and broader. So this broadening of the wings of the line will be part of this physics problem. So you have to include that. Most codes that dealt with type 1A or type 2 P supernovae, they didn't care about electron scattering. It wasn't an important effect. And finally, last but not least, going back to the question of why you may not see features in some cases, even though you may actually have interaction taking place. Is this really great work done by David Brantz back in 2000, where he considered the presence of an external illumination source around the supernova photosphere. How do you have that? It's not ad hoc, right? Well, you could have a shock. You have a forward shock away from the photosphere. At the shock front, you could be generating photons, X-ray photons, for example, that are emanating in all directions. uniformly. Some of those photons will hit back at the photosphere. And the question that Dave Brandt asked in 2000, what's going to happen if you have a really intense source of photons that's outside, external to the photosphere? He did the math. Actually, that was a problem that he could solve analytically in his paper. And then he found out that the stronger that source is, the more you will actually mute the lines that you see from this supernova. Now, he did this problem for type 2P supernovae, which show a characteristic P Cygni line profile. So in this case, you see the P Cygni line profile unaffected in the case of no external illumination. And then you start increasing the external illumination, the intensity of this external radiation. And as a result, not only you're muting, you're weakening the line profile, you can completely wipe it out, or in the most extreme situations, you can flip it, you can invert. You can have blue shifted emission and red shifted absorption in this particular situation. So you have those four effects: electroscattering, top lighting, non-LTE, and non-homologous expansion, which deem those pre-existing codes to study supernova completely useless if you want to do it for circumstellar interaction. And that's a lot of work. Takes a lot of development. One of my postdocs here, Guru, he's going to talk about it tomorrow. He spent most of his first years plus as a postdoc working on adding those this new physics that we need, testing it, debugging it. It's a lot of work. It's not easy. Now, what do we do? What's the end goal, right? So we're building those tools to study the line profiles in the spectra of interacting transients, which means that you have to start with some assumptions. Nothing is perfect, right? First and foremost, you need a supernova progenitor star. You need a massive star. And for many years, I've been using this very popular code called MESA, Modules for Experiments in Cellular Astrophysics, to produce progenitor structures for massive stars. And the nice thing about MESA is that you can do both single and binary evolution. There's a module called MESA binary, where you can involve both the interior structures of two stars in a binary systems, as well as their orbital evolution, and angular momentum transfer, as well as mass transfer evolution. So anyways, we use MESA to produce small models of massive stars all the way up to the point of a supernova explosion. Once we get to that point, there's not many things MESA can do because it's a semi-hydrostatic code, it's a stellar evolution code. Then we port things into another code called Stella, which was developed by Sergei Blinnikov, which is a two-temperature multi-group radiation hydrodynamics code, where we can add a wind or a circumstellar, whatever circumstellar envelope we want, and then follow and model the hydrodynamics of the interaction. So we can get predictions, density, temperature, ion populations, whatever, you name it, over the course of time. So the output from that is one-dimensional profiles of circumstellar interaction for different initial conditions. It will also give you light curves. So you can get predictions on light curves for those interactions. Then once we have those profiles, we just have light curves. We don't have spectra yet at this level. Then the next task is to calculate line profiles and full spectra. For line profiles alone, we have a collaboration with MIT where we extended and worked on this with Aaron Smith from MIT, a code called COLT, which is a multidimensional 1 to 3D Monte Carlo radiation transport H alpha specifically line transfer code, where we included all those new effects that I talked about: non-homology, top illumination, electroscattering, LT and LT. So that will give you profiles of H alpha alone. Now, what Guru is working on, we have an active collaboration with Los Alamos National Laboratory and Ryan Wallegger and Chris Fryer's group there, where they've built Superlight. Superlight is a very nice multidimensional Monte Carlo, implicit Monte Carlo, direct diffusion Monte Carlo, if you want to be accurate, code that's built to calculate light curves and spectra of expanding outflows, of exploding outflows, which means supernovae, or it could mean kilonovae. You could actually do, they've used Superlight to model the evolution of kilonovae, which are non-spherically symmetric, phenomena. Now, what Guru is doing is he's taking that code and he's extending it, and we cannot use the same name as Supernovae because Los Alamos National Lab is very sensitive about export control and naming things a certain way. So we changed it to Superlight. So we work on Superlight, and there's going to be a future version called Superlight Plus, which is actually going to do the hydrodynamics coupled with Monte Carlo radiation transport. Because what Superlight does now, it takes snapshots, profiles from Stella, post-process them. It's a snapshot post-processing code. It does a Monte Carlo in the LTE. Now we've added nebular approximation and all the assumptions that go along with the non-homologous expansion velocity fields and electron scattering, and it gives you a model spectrum. Guru is going to talk more about his models tomorrow. Now, this is a list of models that I've run with MESA, the initial setups that we plan to post-process with COLT, Superlight, to get predictions about interacting transits. So we have A, B, C, and X series models, and they range from interactions with a red supergiant progenitor, a yellow supergiant progenitor, a blue supergiant progenitor, and a progenitor that's completely stripped of both hydrogen and helium due to strong binary mass transfer with another companion. We also have other models with weird density profiles for the CSM. We just want to investigate as much of the parameter space as we can. It's a large parameter space, it takes a lot of time. And we're doing this for a variety of initial conditions, right? We're looking at different supernova energies, the ejecta masses, circumstellar masses, and distance between the progenitor and the circumstellar envelope, as well as different initial mass loss rates. So it's more than 60 models that we've run where we're looking at post-processing with our codes. If you run those models through Stella, you can get some light curves. And here's examples of the A series, the B series, and the C series light curves that you get. I want to focus your attention out here in the C series models, where you have the interaction of a blue supergiant progenitor with different kinds of circumstellar envelopes, and you get some really bright output. 10 to the 44. That's 10 to the 44. That's nominally the limit of superluminous supernova. It's not really set because there's no real limit. There's a continuum of luminosities. The more transits we discover, there's more continuum. However, for historical reasons, if you're a supernova and you're above 10 to the 44 x per second, we call you a superluminous supernova. So you got all kinds of durations and peak luminosities for this particular scenario. And then comes COLT. So my work with Aaron Smith from MIT has focused on using COLT, and my work with Guru has focused on using Supernovae. So I don't want to steal the show from Guru. He's going to talk about Supernovae tomorrow. So I'm going to focus mostly on the COLT results in this talk. So again, with COLT, we can take an initial interaction profile from Stella. We can post-process it and compute models of line profiles. Again, you can do this for 3D geometries too. So if you have a three-dimensional interaction with a circumstellar envelope that looks like Eta Carina, we could also post-process that with and look at how does the line profile change as a function of the viewing angle. You can do things like that with COLT, for example. And all that COLT needs is density, temperature, composition, level populations for the line transition of interest, in this case, hydrogen. And of course, as I said, we have to adjust and expand COLT to include the 4 complicated physics effects that I talked about earlier. So enough with the words, let's show some plots. So here is a model line profile for one of our models. This is the interaction between a red supergiant star and I think it was 0.1 solar masses envelope. We call it model A4. It's from the A series. So in the blue here, you see the line profile at 10 days after the interaction starts. And we're only including the background plus the line photons here. Now, if you also include the electron scattering, you get what you expect, which is that you remove flux from the line center towards the wings, and you get a broader wings for that line. You also, of course, have the narrow absorption feature, which is something I showed you earlier in some of those observations, which is due to the unshocked wind that's further out. That's a low velocity wind. Now, here's another experiment where we test the implementation of top lighting. So in this case, again, you have the blue is the original line profile at 10 days. Then the orange is the original line profile plus electron scattering, where you get the wings again. And then the green and the red include two different levels of top lighting. And as expected, TL1 is lower, less intensity in top lighting. TL2 is more intensity in top lighting. And as expected and predicted by David Branch, the flux of the line gets significantly suppressed by a factor of 3 or so. And the more top lighting you have, the more you suppress the flux of that line. Now, you can do things like post-process several phases of the interaction, and then you can make a movie of how the line profile evolves. So here's the movie that shows you how the line profile of H alpha evolves over the first 50 days for model A4, including all the effects that I just described. And just to make it more visibly pleasant, you can see the different phases here. And you probably also see that there's this blue bump that develops. And that happens right at the point where the shock breaks out from the optically thick circumstellar envelope. You have a big sudden release of a lot of blue photons from the shock. So this is the name of the game of what we're playing, at least part of what we're doing. And just to summarize everything, is very important to have accurate models of circumstellar interaction in order to study a multitude of transient phenomena that is expected to be found by the next generation transient search projects like the SLSNe. We actually, as something I forgot, very important, I forgot to say, is that the earlier, the more we develop the ability to collect spectra earlier and earlier after you discover a supernova explosion, the more we see that circumstellar interaction really is everywhere. Supernovae that we considered typical, like type 2P supernovae, we found some of those supernova hours after the explosion. People have taken spectra 2, 3, 4, 5 hours after the explosion, high cadence stuff, and they found interaction. They found narrow emission lines that then go away, which probably means that you had a circumstellar envelope really close to the progenitor star. It was very small, it got swept up immediately, and then it's gone. And then you have homologous dysfunction. So it's a question of time scales and intensity. Where is that circumstellar envelope? How far is it from the star? How dense is it? What is the composition? What is the geometry of the circumstellar envelope? Again, as you can imagine, the parameter space is huge. And with that comes a natural explanation, perhaps, of the diversity of light curves and spectra that you get when you look at those transients. So a thorough study of circumstellar interaction is predicated on expanding our current numerical tools, which have been built for years and decades with a traditional supernova mindset, with no interaction. So we have to add all this complicated physics to be able to do this problem correctly. Now, the interplay between all those effects and the complexity of the parameter space involved, again, could lead us towards a unique way of explaining a variety of superluminous, all superluminous, maybe not all, but most superluminous supernovae, and a variety of transients for different kinds of parameters that you can look at. So part of our goal is to create a library for as many parameters as we can, a library of models of light curves and spectra that we can share with people in Israel and the Weizmann Institute, where people can look at and compare their future observations against to get an idea of what may be going on with their transient. And that is why it is very important to have this database, because we will be overloaded with data over the next few years. And in some cases, we won't have enough graduate students to analyze the data. So of course, we're going to be using data science and machine learning to do the job. And then the question becomes, it's a question of automation. You find something, you classify something, and then you immediately compare it with a suite of models that we have calculated along with others in the community to have a rapid response, a rapid understanding of really what goes on. And as a side note, it's all about understanding stellar death and what happens to massive stars, how they lose mass in the years, months, some cases days before the blow up. What happens if you add a second star into the system? Now, I didn't talk much about it today, but Shagiv is going to talk about it tomorrow. You could have another kind of category of transients that comes out of having a smaller star merging into the envelope of a bigger companion and releasing some mass. And then on top of that, what happens to the future of stars that have been merged? Today, people believe that more than 60% of massive stars are in binary systems, and more than a third of those binary systems have or will experience a merger at some point in their evolution. So it's a more common thing than we thought. The question becomes, how does it affect rotation rates of stars? Compositions, magnetic fields of stars could be amplified by merger. Mass loss, the evolution of the progenitor of a supernova explosion. So there's all these pressing questions that we can hopefully help address over the next few years with these new numerical tools painstakingly developed over the last couple of years. Thank you so much for your attention.
Thank you very much, Manos, for this talk. Other questions for Manos?
Yes.
So I have two questions. One, can you give in a couple of phrases a physical intuition of why when you illuminate the supernova, the lines go away?
Right. So that's a very good question, actually. Let me go back to the slide right here. So I'll try to put this in as simple of a statement as I can. But basically, what you got here is you have those photons that are bombarding the photosphere. And as a result, you have downscattering. So let's just take a shot, right? You have X-rays. A lot of these X-rays will be post-processed into optical radiation. So a lot of these photons will find themselves in the H alpha region. And eventually, what you will have is you'll be absorbing where you're supposed to be emitting, right? So you're emitting photons here, but you'll also be absorbing photons here. And the counter effect of how, if you have more absorption because you have a stronger source, then you have emission from here, you will add more flux towards the emission side. So that's kind of like in a nutshell, as simply as I can put it. But I'm one of those people that speaks better with numbers, so I can point you to the paper as well. It's a very simple derivation.
Okay, but this explains why you suppress the emission part. How do you fill up the absorption part?
This one?
Yeah.
Well, because when it comes, let me think about it for a second. Let me see. Okay, how do you fill up the absorption part? So you add more flux here as well. It's a good point. I need to think about it more.
Okay, may I? Okay. So how can polarization help you in the models?
Okay, thank you very much for that. I mean, that's part of the reason I came to this, right? Yeah, of course. It's kind of like the theory conferences where people will always ask you about rotational magnetic fields. So,
he does that.
okay. All right. So yeah, polarization. So obviously, a lot of the things that I showed you earlier are highly non-spherical. So having the ability to do rapid follow-up of transients that are discovered by PDF or ZPF or PanSTARRS, other search projects, to get some polarization data early on, as early as we can, to determine whether there's a significant polarization level and how that polarization level evolves over time will help us see whether there's aspherical interaction. As a matter of fact, one of those two events that I showed you earlier, not this one, but the other one, PTF11 IQB, has polarization measured. I think I sent you the papers for that, the Basso. And they actually are detecting polarization early on, which helps them support the case they're making for this model. So you expect about 2%, 1 to 2% polarization, background polarization levels. That's what they see for all of these things. And you also expect significant line center polarization early on. So if you can do that with Roboball, for example, then you can help us understand what the shape of this interaction could be early on. How many are spherical versus aspherical? At least that, what's the fraction of spherical versus aspherical interaction?
Okay, but if you wait long enough, eventually you have other evidence for sphericity, right?
Well, no, not if you have something that's 100 megaparsecs away.
100 more.
Yeah.
Spectral.
So it can get really hard. But you have the other side of this question as well. You could have a situation where you have an envelope that's completely detached and removed from the progenitor, and then the ejecta catches up with it a year after the explosion. So you see supernova goes like this, and then a year later, whoop, starts brightening up again because the ejecta is catching up with the lost envelope. So maybe in this later case, you could also determine, what the polarization and geometry of that interaction looks like. I mean, that's a question for observer. I'm just giving you the predictions. You guys determine whether it's feasible or not.
So you mentioned about the shock breakout.
Mm-hmm.
So how much of a delay do you expect for the shock breakout because of the stellar activity? But this is critical for catching it. And,
Right. Very good question. So that depends on how optically thick your circumstellar envelope is. So I cannot give you a unique answer. It's going to be 1 day, 2 days, 3 days, it'll be up to 70 days in some cases. That's the case for Rho 61. Yeah, I have a really bloated envelope, very optically thick shell. So yeah, again, it's a zoom. Depending on how much mass.
So there can be enough warning for.
Oh yeah. You see something growing for a long period of time. And then at peak luminosity, usually peak luminosity in the circumstellar scenario usually coincides with more or less with the breakout of the shock.
And follow-up prediction question. We have prediction for the X-ray emission from the shock breakout.
Right. So, but
they're very prompt.
Yeah, unfortunately, we don't have many for this. I'm talking about superluminous supernova. We have, 5 or 6 handful of superluminous events where they've actually been able to detect enough flux with with Chandra. But they are building the new, decadal survey, the new generation X-ray telescope should be able to do more. Now, gamma rays actually are more interesting. They're even harder to measure because the two competing models that you have, magnetar versus circumstellar interaction, events. The one prediction that makes them different at late times is the gamma ray flux, the high energy gamma ray flux, Fermi-Lab flux. So if there is, and I'm not aware of any future projects of this high energy gamma ray direction. I'm sure there's some under development, but if we manage to find some gamma ray photons at 100, 200, 300 days after those explosions, and they're at the level, they evolve with slopes not expected from shock emission, then magnetars make the way. So that's the more direct way to break the photon.
Maybe a simpler question, right? One thing is to do, with the work that if I understood correctly, that you are doing with stellar, right? You basically take as input data from an explosion, you treat them, and you make a prediction in terms of spectral evolution.
Yes.
Right? So this is something that was not done readily in the past. Right?
Yes.
Is there a statement that you could make, which would be along the lines that the prediction that the previous models were making on how red supergiants will explode or whatever?
Well, we're not looking specifically at the explosion mechanism here.
I mean, is there a prediction that was done in the past that through today's analysis, you can say that was probably wrong? Right? Just because we have more data now and we can analyze it better.
Right. Well, you take the circumstellar direction of the picture, you're probably going to miss out on some effects. For example, one that comes to mind immediately is the calcium H and K lines, high velocity features that you see in some type 1A supernovae. Where for many years, people would see those features for a subset of events, but they were unable to reproduce them with their traditional codes. So they fudge their way around them, but one way that this is resolved is if you actually have some sort of interaction. So you have a new category of supernovae of type 1A supernovae called type 1A CSM, now that we know are undergoing some sort of interaction, which can explain those transformations into high velocity features in the spectrum. So that's one that comes to mind immediately. But I haven't thought of anything else that may be affecting directly either the ideas we have about mass loss for red supergiants or the explosion itself.
And also along the same lines, right? You are studying unique events. The explosion happens, material is swept out, etc. You analyze it and explain what the environment might be, how it's interacting with the presenting stuff. Could you apply your code in events in novel, where you have a more, where you have a periodicity, so that you could actually do, validate your code better? Because it seems to me that now you have I know that it's a completely different energy levels and time scales. The time scales are shorter. Yeah. Right? So the question for me is that, you say that there is a zoo with the ISMs to complex the binary stars and whatnot. So you run a suite of models, and you can always find a model that is close enough to the observable. But this is possibly a plausible scenario from what has happened, but it's not necessarily a unique solution, right? Because
the generosity of,
yeah, exactly. If you were, would you be able to apply your code in a periodic phenomenon where the reason why you have an explosion is a well-known interaction? That would, but the environment would evolve towards a way. So what I mean,
at some level, we've already done that. That's part of our testing. So what we've done is after we've added all this new physics with interaction, we run regular supernovae models, type 2B, type 1A, and our solution converges to the solution we would expect. Whether the assumption were not there. That's kind of like the way we benchmark and test. Or we go for, one thing we want to do is go from LD to LD and see whether we converge on the LD solution expected for a known scenario. So we've done other tests that are more direct to what we're looking at, but not novel. We haven't looked at novel or partial explosions.
Yes. More important technical question. You showed the broadening of the line due to scattering. Can you? Yes, that's it. That's it. Why do you pin all the curves to the top of the line?
This is not something I've done. This is done by Prof and Casey. So I think they just did it for scaling, for visual kind of.
Okay, scattering preserves the number of
right. So in reality, it would drop.
It should be down.
Right, but I think they scaled it artificially to show the effect.
It says individually normalized.
Yeah, individually normalized.
Ah.
Yeah. So if you go to my prediction with COLT, you can see the effect.
Okay.
Got a question?
Yeah, so you're sort of trying to explore the effect of CSM interaction when you have like a normal kind of explosion, and then trying to compare it with the predictions from, say, McIntyre model or the fallback, accretion, etc. But in those other scenarios, the difference is going to be that you have a different sort of energy input for the explosion.
Right.
But they're probably also going to interact with CSM.
Right. A hybrid model. Yes.
Sort of a,
reality is always more complicated. Isn't it? So, I mean, we are focused. So what's unique about CSM interaction is it's very effective way of converting kinetic energy to luminosity. You can get really bright transients effectively with shocks, broadly speaking. Now with magnetars, Other experts in the field, like Brand Metzger, have done a very rigorous analysis, and they found that actually there may not be as efficient in converting energy to high luminosity as originally thought, if you take into account the microphysics and all the microprocesses involved into the wind-blown region versus the ejecta, for example, or the presence of jets that you could have if you have a magnetar. So in principle, it wouldn't be hard in Supernovae to add a blue source in the middle of your grid that declines with an analytical prediction that was provided by other authors. You could do that. You could add sources and see what happens. That's sort of the game that Luc Descartes has played, for example. But if you want to do it rigorously, and if you want to, you pretty much have to merge what we're doing with what Brian Messer has done, which is two PhD theses together. It's not going to be an easy task. So we're focusing on this model. We have looked at peristability. It's a simple model. Peristability is very simple. It's simpler than any other supernova explosion mechanism out there. But we have not had the time or effort to put in the magnetar. We'll let other experts do that. There's one.
I don't have a question, but I have a comment. So while we were talking, probably people understood it, but just to clarify, the code written by Lawson paper is called Superluminous, and our code is called Superluminous.
Oh yeah, sorry, Supernova was not here. Yes.
Yeah. So when you were speaking, you said Superlight was developed at Lawson. So
yeah.
just want, probably people got it, but just want
Trademark by Guru.
So we cannot use name Superluminous for our code, and Superlight is actually different than Superluminous, which I'll talk about tomorrow. But our code is Superlight, and Lawson code is Superluminous. Right. Just to clarify.
Thank you.
So I have a small question.
Yes.
So if we go back to the stellar light curve models, how much of that luminosity is due to nickel? And,
Minimal. So all those progenitors.
But you could track the.
Yeah, definitely. Stella includes the input that you will get from the nickel, but it's minimal. Typical values 0.05, 0.06 solar masses of nickel 56. And it's going to be important at the very, very, very late times. So this phase, the bright phase, the photospheric phase, is dominated by the interaction. Then later on down here, you may have a little bit of nickel.
Okay. I have a question.
Very small question. Organization. I will ask another one. Put on my cosmologist hat.
Okay.
Since I'll ask a question for much easier system. The one that you use for testing, supernova type 1A.
Oh yeah. Okay.
Right. Okay. So, in your expert opinion, as a person who runs supernova simulations from scratch and the evolution libraries, with what confidence would you say that there is absolutely no chance that the fundamental relation in cosmology, which is luminosity versus,
You really put me on the spot here. I don't know if I want to make a statement of this
it does not
controversial issue.
You have tenure, don't worry about it.
Okay.
That's why we are asking you.
No, this is a safe environment.
Exactly. Yes.
We're not recording anything.
Okay.
Actually, this is a live. We are recording it, but
Okay. So as you well know, there's two competing models for type 1A supernova. Double degenerate, single degenerate. And even between those two communities, I've seen crazy fights, like in conferences back in the day, before they had codes of ethics. I've seen all kinds of things. So now you're taking the next step, and you're asking how standardizable are type 1A supernova, and how robust the curve of the luminosity distance relation Hubble plot is. Well, I mean, again, I'm not quite the expert in type 1A supernova because I work mostly on labs. But what I hear through the broken pipe is that, if you have a double degenerate scenario, for example, some leftover mass, which can affect the light curve, which can affect the range of peak luminosity, how sure you can be about this is the peak luminosity. There's also questions regarding to the survivability of the whiteboard, and whether you have some sort of like lateral mix-up if you have an off-center explosion in the white dwarf, you could have a shock wave that propagates around the white dwarf surface and then merges on the other side. And that might affect the evolution of the ejecta, and thereby, the evolution of the ejecta and the geometry of the ejecta can affect the peak luminosity that you get in different times. So that's kind of like what I hear from the broken pipe. Okay, and then of course there's the question of how sure are we that it's 1.4 versus 1.3. I've heard all kinds of things. Now, has this been resolved? The answer is no. Just people are still talking about it. Just to find out. I hope that answer is still there.
Wouldn't it be nice to have a probe that does not depend on supernova?
Exactly.
If only that were possible.
If only that was possible.
Okay, then let's take those three again.